Hello, this is Dr. David Kreller of the Department of Chemistry of Chulalongkorn University in Bangkok, Thailand. I'm here with the second installment in this series of videos which cover the content of the first chapter of the Raymond Chang chemistry textbook, which is available from McGraw-Hill Publishers and is currently in its 13th edition. In this second video, I'm going to talk about solids, liquids, and gases. This video should be sort of short. This video is available to anyone who studies chemistry and who finds the video on YouTube. But I specifically made this video to support the students of Gen Chem 1 who are currently in the Bachelor's of Science of Applied Chemistry program at Chulalongkorn. In the last video, we talked about a classification system where we look at samples of substances and classify them into elements, compounds, and mixtures according to their composition. This is a second classification system which is completely independent of the first. In this system, we talk about the classification of samples of matter into either solids, liquids, or gases. Now, this classification system is completely independent of the first classification system that we talked about. Just like, for example, imagine two systems for classifying all the students at Chulalongkorn University. The first system could be according to gender, and of course the students are divided into those that are girls and those that are boys. And the second classification system might divide them into groups according to the year of university: first year, second year, third year, or fourth year. And that's completely independent. A boy could be first year, second year, third year, or fourth year. It doesn't matter. Just like an element could be solid, liquid, or gas. So in this classification system, we simply classify the matter into solid, liquid, or gas physical states. And as we will discuss in this video, there's important differences between the states, and these important differences always relate back to how closely the particles that make up that substance are packed, and that controls its density. Then the amount of order that is present in the way the particles are packed and arranged. And they differ in terms of the nature of motion of the particles. For example, here's a little picture of a solid. And by the way, I have to mention that I got these animated pictures of the solid, liquid, and gas phases from the website. I'll give them the credit. Purdue University General Chemistry. Okay, so here's a solid, here's a picture, animated picture of what's going on at the chemical level in the solid. Now those particles are strongly bonded to one another. Because of that, they stick closely to each other. So this phase has a high density. The ratio of mass to volume is pretty high because it occupies a limited volume because they're so closely packed together. And those particles are not able really to move around a whole lot. Each particle stays more or less in its fixed position. Maybe there's some vibration around the position of each atom. But the solid may have some motions, but it's more like collective motions of atoms moving together, as the solid has vibrations within it, as opposed to the liquid phase. Particles are having some bonds to one another, and so they keep relatively close to one another and form a phase that has relatively high density. But there's a lot less order in the liquid than there is in the solid. And so at the chemical level, you can see them moving around and they have more motion. They're still relatively close to each other, but they're able to move around so much that they can slide past one another, and it is for that reason that the liquid can flow. Contrast that with the gas then. In the gaseous phase, the particles are far apart. They're not really bonded to one another, or if they have some bonds to one another, there's so much energy has been put into the matter that the particles have so much energy of motion that they are able to overcome the energy associated with the bonds. So they're moving around freely, and they occupy a lot of space. There's quite a bit of space in between them, and you can see that phase has a low density because the mass is distributed across a relatively large volume. And there's very little order. Actually, there's pretty much total chaos in there. The particles are all moving in random directions, and as we'll discuss in future videos, the particles can have a real range of velocity. They're not even all moving with the same speed. There's chaos in that area as well. And so now let's talk about the changes between these states. Of course, you may already know that a solid can be transformed into a liquid. And in terms of energy, do we have to put energy into it or take energy out of it to go from a solid to a liquid? Do we have to break bonds or do we allow bonds to form? I'll just leave those as rhetorical questions for you to think about. We can transform a solid into liquid, and conversely, it's reversible. We could change a liquid into a solid. And so what are the names of these phase changes? Think about that. Okay, a liquid can be transformed into a gas in principle, okay, and it's reversible. A gas can be turned back into a liquid. Also, a solid, in some cases, can turn directly into a gas. Do you know the name of that process? And if the solid can change into a gas, then the gas can reversibly change back into the solid for those example materials that are able to do that. Anyway, the phase changes are called melting, to go from a solid to a liquid, or freezing, to go from a liquid to a solid. To go from a liquid to a gas is called evaporation. To go from a gas to a liquid is called condensation. To go directly from a solid to a gas is called sublimation. And then to go directly from the gas to the solid is called deposition. Just a few more slides to summarize the main attributes of solids, liquids, and gases. So the solid, in summary, particles are bonded relatively strongly to each other and stay in fixed positions. So as a result, you cannot move through a solid. It's impossible to move your atoms, the atoms of your body, through the atoms of the solid, because that solid matter is dense and the particles cannot move past each other. They're stuck in fixed positions, and so you won't be able to move through them. Try walking through a solid wall, for example, if you need that to be proven to yourself. So solids maintain their shape at room temperature. They do not flow, in other words. For example, the pen or pencil that you are using at school, or maybe taking notes right now, has the same shape as it did yesterday. It didn't flow to conform to the shape of the desk that it's sitting on or the shape of the bag that it was stored in. Solids do not change shape. Okay, and the bonds that are holding a solid together could be chemical bonds between atoms, such as in diamond, where all the carbon atoms in diamond are chemically bonded to one another, or the bonds could be strong intermolecular forces, such as in polymers like plastics. We'll summarize the liquid state. Individual particles are relatively strongly bonded to each other, so that they create a condensed phase, occupying a relatively small volume and hence having a high density. But the particles have more freedom of motion. They can actually flow past one another. So you can move through liquids, such as when you go swimming. The matter that makes up your body can move through that matter, because to move through that matter, involves having those atoms sort of flow past each other or separate and then recombine as you move through them. So when you go swimming, you actually fully experience some of the properties of the liquid. The relatively high density provides the physical buoyancy that holds you up, and the fact that the particles have more freedom of motion allows that liquid water to flow, slosh around, have waves and things like that, and you can move through it because those particles can slide past one another. So liquids do not hold their shape at room temperature. They flow. They take the shape of the container, such as the swimming pool or the beaker or your bottle of water that they are placed in. Finally, the gaseous state, in summary, do not hold their shape at room temperature. If it's a gas at room temperature, or at whatever temperature you've had to elevate it to force it into the gaseous phase, it will not hold its shape. actually, those particles don't stay in one place, as we have mentioned. Gases will escape unless trapped in a sealed container. So particles of the matter that make up the gas, whether they're atoms or molecules, are far apart and are always moving. And that's why they escape. They will keep going off in a straight line until they bump into either another particle of gas or the sides of the container that's holding them in one place. And if there's nothing there for them to bump into, they will just travel off in a straight line and not look back. So gases are actually mostly empty space, which causes them to have low density, and they can be compressed. You can take the gas and usually decrease the amount of space that that gas occupies. And there's so much space between the atoms in a gas, and they're not bonding to one another, and as a result, you can move around easily within gases. For example, when you walked into a classroom, or you walked into the room in which you're watching this video, you actually moved through gases, the mixture of gases that make up our air. And it's very easy to forget that gases are even physically present. Actually, it's only under special circumstances, such as when there's a strong wind and we can physically feel the force of the gas as it bumps into our body, that we really become aware that the gas is actually there. Okay, that brings me to the end of video number 2 in this series of videos that cover chapter 1 of the Raymond Chang textbook. Thank you for watching, and thank you for listening, and thank you for learning.